Hi SAT prep students, this is Miss Baker. I'm back with another math lesson. Today we are continuing our lessons on circles and we are specifically going to be discussing arcs and chords. So there are three theorems we're going to go over that talk about the relationship between arcs and chords. So in the same circle or in more than one congruent circles, congruent arcs have congruent chords. So if we have arc AB and arc CD in the figure you see here, and those two arcs are congruent, then the chords AB and CD are congruent as well. So if arc AB and arc CD are congruent, then segment AB or chord AB and segment CD or chord CD are also congruent. And you can say that the converse is also true. Theorem number 2 tells us that if a diameter of a circle is perpendicular to a chord, then it bisects that chord and it bisects the arc. So if segment CD in the figure you see here is perpendicular to segment AB, then AE is congruent to BE and arc AC is congruent to arc BC. So if you have a diameter of a circle and it is perpendicular to the chord, it needs to be marked though. Make sure you see that there is the little right angle symbol indicating that this diameter is in fact perpendicular to the chord. That's not always true. So look for that symbol. If you see the symbol that the diameter is perpendicular to the chord, then the diameter will bisect the chord and bisect the corresponding arc. Here's the third and final theorem regarding arcs and chords. In the same circle or in congruent circles, chords that are equidistant from the center of the circle are congruent. So, in the image you see here, you have, we have this segment going from the center of our circle out to the chord or segment CD. Then you have this segment that goes from the center of the circle out to the chord or segment AB. And they are marked as being perpendicular. Okay, the segments are perpendicular to the chords. If they're perpendicular, remember from the last theorem, then that means that this little segment CF and this segment FD are going to be congruent because it bisects the chord. Same thing down here, this would be bisected. What they're telling us here is that in this circle, if these chords are equidistant from the center of the circle, then the chords are congruent. So if these two little segments, OF and OE, are marked as being congruent, then you can say that CD and AB are also congruent. So if OE and OF are equal to one another, equal in length, then AB is congruent to CD. Those are the chords. And you can also say the converse of that is true. Okay, let's go through example number 1. In the figure below, if the measure of arc AB is equal to the measure of arc CD, and both of them have the same measure of 110 degrees, and we also know that chord or segment CD is 15, what is the length of AB? Okay, so they've told us that arc AB, which is right here, that measures 110 degrees. And arc CD, which is down here, measures 110 degrees. So these two arcs are congruent. The segment AB that corresponds to arc AB, and then the segment CD, which corresponds to arc CD, they're going to be congruent as well because the arcs are congruent. So if the arcs are congruent and the segments are congruent, and then we're told that this segment or chord is 15, then clearly this other segment or chord will also be 15. So arc AB is congruent to arc CD. Therefore, segment AB is congruent to segment CD. If segment CD is equal to 15, then AB is also 15. Here is example number 2. In the figure below, segment AB, which is a diameter of the circle, is perpendicular to segment CD. Segment CD is a chord of the circle. If AB, the diameter of the circle, is equal to 20, and CD, which is a chord of the circle, is equal to 16, what is the length of OE? All right, so I told you segment AB is the diameter of the circle, and it measures, if it measures 20 in length, the diameter, then what's the radius? Well, the radius is half of the diameter, and the diameter is 20, therefore the radius is going to be 10. Okay, that's good information to know, because we are going to create this right triangle, and the hypotenuse of that right triangle is a radius of the circle. The radius is equal to 10. The right triangle we're looking at is right triangle CEO or OEC, however you want to name it. But because we know that the hypotenuse is a radius of the circle, and we know that the radius is 10, we can mark the hypotenuse as having a length of 10. We are also given that the chord CD, which is right here, this chord has a length of 16, and we see that the diameter is perpendicular to that chord, so the diameter is actually bisecting segment CD. If CD is 16, then half of that is 8. This segment, or this side of the right triangle, is half of the chord CD, which means that this side is also, it has a length of 8. So now we know that this side of the right triangle has a length of 8, the hypotenuse has a length of 10, and we just need to find the length of side EO or OE. They want to know what is the length of segment OE, which is right here. So if we use the Pythagorean theorem, we have the equation 8 squared plus b squared equals 10 squared. 8 squared is 64, 10 squared is 100. So we have 64 plus b squared equals 100. Subtract 64 from both sides and you get b squared equals 36. Take the square root of both sides and you get b is equal to 6. So b is equal to 6, which means that OE is equal to 6. Let's look at example number 3. In the figure below, we have this circle going from the center of the circle out to point E, OE, and OF from the center to point F. So here's OE, here's OF. OE, this segment, is the distance from the circle to chord AB. And OF, this segment, is the distance from the center of the circle out to chord CD. They are equal length. They have equal lengths, which means that AB and CD are equidistant from the center of a circle. And one of our theorems told us that if two chords are equidistant from the center of the circle, then those two chords are congruent. We know that. So we know that AB and CD are congruent because they are equidistant. The other thing we know is that these two segments are perpendicular to our chords, meaning that they bisect both of the chords. So AB is being bisected and CD is being bisected. The information we also know is that BE is 12. So half of segment AB is 12. So then that gives us the overall length of AB, which is 24. So BE equals 12. Therefore, AB equals 2 times 12, which is 24. If AB is 24, and we know that AB and CD are equidistant from the center of the circle, then we know that the length of AB is the same as the length of CD. So if the length of AB is 24, then the length of CD is also 24. That concludes our lesson on arcs and chords. The next lesson is the last lesson on circles, and it is regarding circles in the coordinate plane.